Welcome to the 7th episode in a series where I'm doing a total rebuild of my cheap CNC3018. This episode is going to focus on how I made my DIY controller for my DIY CNC, and I'm going to break it up into a couple of sections so people can skip around as they like. First, there's going to be a general discussion about making a DIY controller for your CNC, and then I'm going to give you a bit of a look at the controller board that I made, as well as the enclosure I made for it, and also how it's mounted and wired to the CNC itself. And finally, for those of you still interested in hanging around, I'm going to do a walkthrough of the controller settings that I'm currently using with my CNC. Alright, so that's about it. Let's get into it. So I did this first section, hopefully to help people who are looking at how to source a CNC controller, be it as an upgrade to your existing CNC, or a controller for a new DIY CNC build, or rebuild, as in my case. Obviously, if you have a major brand CNC, then you probably should look at seeing what sort of upgrade options your original manufacturer might offer. But beyond that, it seems there are probably only 3 options to consider. The first option is to buy an off-the-shelf pre-built controller, and actually there are heaps of them on AliExpress. They're pretty reasonably priced, and you can buy them with or without stepper motor drivers included. If you go down this route, do your research, look for a seller that sells a lot of these units and has good reviews, and make sure you get a 32-bit variant. I do not recommend using an 8-bit variant anymore. The second option is to use a CNC shield combined with a mainstream microcontroller board. This is one here that I had bought for an Arduino Uno some time ago. Actually, it's pretty cheap. I think it only cost around about $2 for this shield. But here again, I would recommend sticking to a newer 32-bit variant of a microcontroller if you're going to do this. But unfortunately, a quick search on AliExpress didn't give many results for the 32-bit microcontrollers that I have on hand anyway. I think there are some private people selling shields. I saw something on GitHub, some sort of designs that people had put out there. So if you search hard enough, you're probably going to find something that's going to work. Anyway, it doesn't really seem like an easily accessible option anymore. Not like this old Arduino Uno shield that was pretty common in the past. And finally, the third option is to build something yourself, which is actually what I did. There's also a bit of a hack or a hybrid option of using the second and third options together. And at first, that is actually what I was thinking of doing. So in my case, I was thinking of using the Arduino Uno CNC shield with an adapter PCB that would allow me to use one of my 32-bit microcontrollers instead of the Arduino Uno. This is sort of similar to what I did with my mini lathe project, where I adapt an Arduino Uno display shield to work with the BlackPill. But I actually gave up on this idea pretty quickly because physically it's clumsy and messy having all of those 3 layers of boards stuck together. And actually, if you look at the Arduino Uno shield, there's really not much to it, so it just makes sense to make your own adapter shield from scratch. So that's what I decided on doing. Building it for one of the 32-bit microcontroller boards that I already had on hand. And I can tell you it wasn't really an easy or obvious choice. I did spend a lot of time researching and weighing up the various options before coming to this conclusion. And let me give you my reasoning why I came to this conclusion. Firstly, I wanted to be more in control of the firmware. So that meant sticking to a more popular microcontroller board, along with more commonly used open source firmware for it. Now, some of the off-the-shelf controllers might also work with open source firmware, but I just don't have enough information to make that judgment, so I didn't want to risk it. And the second point that drove my reasoning was form factor. I wanted to fit in a very limited space on the back of the CNC where the old controller went, and I didn't really want all the extra unused connectors that typically come with generic shields or off-the-shelf controllers. And finally, of course, was cost, as I've made pretty clear consistently with this project. I'm trying to keep the costs as low as possible. As for the open source firmware availability, I was actually going into this with pretty limited knowledge. I think I'd done some research in the past that showed me that the grblHAL firmware was readily available for the Uno and the shield that I'd purchased some time ago, but really that's about all I knew about the situation. So the 32-bit microcontroller boards that I had on hand are the STM32F103 BlackPill, the STM32F401 BlackPill, the STM32F411 BlackPill, or the ESP32W Room. So I actually had a bit of a hunch, possibly wishful thinking, that the grblHAL firmware would already have been ported to one of these pretty popular microcontrollers, and thankfully a quick search on Google proved that to be correct. What I found was an excellent project on GitHub called grblHAL, where heaps of popular 32-bit microcontrollers are all supported from a common operating core. And the nice thing is that it also seems that a number of CNC manufacturers are also making use of this project for their CNCs, so it generally looks pretty well supported, and it's probably going to hang around for a while. There's even a nice web interface where you can easily navigate to find what you need, and it allows you to simply download the binary file that matches your microcontroller and required configuration. Actually, it's super convenient. So at first I was going to cheap out and use my $2 F103 BlackPill, and honestly I thought that would be good enough given that it at least has 10 times more performance than the Atmega 328P. Even the 328P version was doing the job well enough, well, at least most of the time anyway. But unfortunately, it seems that the BlackPill version of the firmware is now frozen, and that seems to be due to a lack of memory, so they're unable to add new features that come with the newer versions of the grblHAL core. So that means that even though it's frozen, it'll probably still do the job just fine, but it would be cut off from new possible features that might come out in the future. And something else that sort of tilted my decision-making process away from the BlackPill was that I'd found out that the BlackPill actually has a hardware-based floating point capabilities that grblHAL actually makes use of, whereas the BlackPill doesn't have that feature. And in theory, that itself should mean a huge improvement in performance when comparing BlackPill over BlackPill running this system. So I chose to go with a $4 F401 BlackPill in the end, paired up with some TMC3018 stepper drivers. I could have also used the $8 F411 BlackPill that I had on hand. It's a bit faster too, and it even has a bit more memory. But really this started to look like a bit of overkill for this project, and would unnecessarily drive up the cost of the project too, which I didn't want to do. And of course I could have gone down the route of using the $6 ESP32, and I do notice that many of the pre-built Chinese controllers are actually using them for their core processor. Now I actually use the ESP32 in my solar project, I don't know if you've seen that, but overall I was pretty impressed with both the performance and the capabilities. Generally speaking, it was much better than I expected, and really quite an amazing value proposition. But it lacks IOs, and it's really not quite as stable as what I've experienced when using an STM32 series of chips. Anyway, having locked in the microcontroller board that I was going to use, the next step was to download the firmware, load it up, and test it. And it didn't work. In fact, I couldn't get the controller to communicate with the grblHAL control software at all. I then went ahead and tried the F103, the F411, and still no go. I couldn't get any serial response over USB. It just seemed like nothing at all was happening actually. And then I had a thought, what if I needed to ground the E-stop pin? So I tried it, and it worked. Now, I really can't explain how frustrating and a stupid problem this was that I'd wasted so much time on trying to solve it. And after digging a little bit, I did actually find a mention buried in the documentation, which of course I didn't read in advance because I'm not the documentation reading sort of guy. That's half my problem. But anyway, from a software developer's point of view, having it started a non-responsive way, if the E-stop is simply just not grounded, is a stupid way to do it. I mean, you could have at least sent back some sort of error response or any type of response. Anyway, I guess that's my rant for this video. So once I got the E-stop grounded, I found that all three types of the STM32 boards that I had now worked fine with their respective firmwares and communicated no problem at all with the grblHAL software that I was working with. So that meant I could move on with building the board. Now it's also important to note that there are a couple of different versions of firmware out there for each of the different microcontrollers. It seems that the enabled features differ somewhat in each of the versions, but for me I just wanted it to be minimalistic, so I just chose the most basic version. But even with the most basic version there were two options, and the difference was only just the way that the IOs were allocated on the microcontroller board. So anyway, I just chose the one that I thought would be the easiest to hand wire. Now fundamentally there's bugger all to making one of these CNC shield adapters. You just need a way to get the power into the board at the right voltage to drive those stepper motors and the microcontroller. In this case I decided to reuse the original 24 volt power supply that came with my CNC3018. For each stepper motor driver you need to have a pin header socket, a 100 microfarad 50 volt electrolytic capacitor with a decent operating temperature range, and some jumper pins for configuring the microstep resolution. You also need a connector for connecting to all the various parts on the CNC, stepper motors, end stop sensors, etc. And you need a pin header obviously for the microcontroller board itself. You're obviously also going to need a way to power that microcontroller board or any of that 5 volt or 3.3 volt logic, so you need to figure out some sort of power regulation type scheme. So you can't just use the 24 volts for the stepper motors and plug that directly to the microcontroller board, you're probably going to kill it, so you need some other way to step that voltage down. And optionally, you can also add some IO protection for the things like the end stops, so you're not plugging that directly into the microcontroller, be it optocouplers or a simple logic buffer IC. So here is all the collection of the parts that I used for the build. I'm not even going to bore you with the circuit diagram because I didn't even bother drawing one. It's really that simple. I just looked at the pinouts and just wired it one by one. It's very, very straightforward. And I didn't even bother filming me hand wiring the board because, well, that's boring and no one's really interested in watching that, so we'll miss that this time. So with all that said, let's take a look at the finished controller and how it all came together. So I've managed to finish this board. As you can see, it's looking pretty good. Give you a look at the bottom here. It's not too bad. Could be worse, I guess. Just to step through all of the bits and pieces. STM32 BlackPill, it's a 401, so the lowest spec BlackPill. We have the step down converter, so it takes 24 volts in and steps it down to the 5 volts so that it can run this system in here. we have the 3 TMC2209 silent stepper drivers. So these are rated, I believe, to run at a constant 2 amps. And I had to set up the VREF using the little potentiometer here and using the calculation to figure out the VREF. It's quite interesting because the original unit that I was using, this one here, I actually used more powerful stepper motors. Probably the original stepper motors were 0.9 amp stepper motors, and then I switched it out to the 1.5 amp stepper motors. But you know, I'm a newbie on this stuff. I didn't really know what I was doing. So even though I'd switched to the larger powered stepper motors, undoubtedly the way that these stepper motor drivers work, it was already limiting the current to 0.9 amps anyway, so it's a waste of time. So anyway, I've set this up so that it will run the full 1.5 amps, and I'm using this 74HC573 as a buffer chip so that the inputs from the touch sensors and the end stop sensors and also the emergency switch, all of those pass through this chip before going to the BlackPill, and the output from the BlackPill to the PWM connector also goes through this chip. So that means that if something happens on the outside here, there should be something in the way before it destroys the BlackPill. I mean, the BlackPill's not that expensive anyway, but anyway, it's good practice. And the reason I didn't use a optocoupler here is because optocouplers are really very, very slow. And if you're doing anything at speed, it will actually take a while to actually feed the signal into the microcontroller. And that means you could actually cover a lot of distance in that time. So I think the idea of using an optocontroller is not a good one. I mean, yes, it sort of works, but it's not really the best way to go, I think. So we have the stepper motor connectors here for the X, Y, Z, and we have the emergency switch input here. We have the 3 axes end stop sensors, PWM connector, the probe I put on this side so I can easily access it, and there's a fan 5 volts. Just on the top here I have these 2 LEDs. This LED here is to indicate that the 24 volt supply is present. It's actually driven from the 5 volt rail, but this 5 volt rail step down converter won't be running unless it gets to 24 volts anyway. And there is a 3.3 volt LED just to show if the microcontroller is receiving power. Not entirely necessary, but it just lets me know what's going on with the power situation. Yeah, so alright, so I've already made a case for this, and I have to say I feel I'm getting a little bit better at this. It didn't take that long to do. I have a good sort of process to do that. And I actually got away with doing minimal garbage prints. This is some of the garbage prints here. So really only one bad print for each component, which is not bad. Usually I'm getting about 2 or 3 bad prints, so obviously I did something a little bit better in this process. So here's the base, and I'll just give you a quick look at that. We have the 3 mounting connectors here, which will mount onto the 2020 rail, which is basically the same as what this was doing before as well. And there's only 3 because I want to really push it as far to the edge of the rear of the gantry as possible so that I can easily access the connectors here. So I've tried to make the case as sturdy as possible, which is why I also have these ribs in here to increase the sturdiness without having to print all this infill. And I've split it here along the line where the LED sort of goes. And what else have we got here? Also, I'm using these little black standoffs this time because instead of using a 3D printed mount, which I had done in my mini lathe, the 3D printed mounts mean that these have to be a bit bigger, and that sort of robs you a bit of space on the board. You have to be more careful, which I wasn't when I made this board. So using these pre-manufactured stops make it work pretty good. So let's take a look at the top cover. This is the top cover that I printed. I printed it face down, and that means I actually use something I hate using, which is supports. One of those rare occasions I've used support, and it worked better than expected. You can sort of see where it sort of stuck to the surface here as well. So when I took the support off, it was actually pretty nasty finish, and I had to use a file, and it's still not a perfect finish. And after using a file, it sort of goes a bit white, and so I wanted to deal with that. So I've actually just painted it. You know, and I think that using the supports have worked, really pretty good in this case. I don't think I would want to have printed this in 2 separate pieces and glued it together. It would have looked messy, and there's all of these complex sort of interconnections here between this connector and that. So yeah, I mean, it's a bit of a sacrifice having the finish, But amazingly, the dimensional accuracy is really good. Let's just see if I can get it on here for a second. I haven't got that screwed in, so. But you can see that it doesn't like have any warping or anything like that, and the fit is really very good. I'm really very happy with it, actually. And the last piece of the puzzle is the fan holder here, which we will get to setting up in a second, which goes on there. It's a bit of an ugly sort of addition to be sitting on there, but I wanted to have the airflow on the outside so that it's blowing air onto the heat sinks and blowing it out to the outside, as opposed to this. As you can see, all the dust and garbage in here. I don't even know where the air is going in this. So here's the controller all mounted and everything wired up. I'm also using 3D printed cable management parts like I did in the past to keep everything tidy. The cables also run down the right side upright for the Y-axis stepper motor and Y-axis end stop. You can see how I've run the E-stop and X-axis end stop cables here under the gantry. Also got the Z-axis end stop wired here. The black wire is the earth wire, which earths the whole assembly, and the yellow wire is the return wire from the sensor. And all of the Z-axis wiring makes use of my original CNC3018 customizations that I had before to get the wiring from the Z-axis assembly across to the gantry. Yeah, so cabling wise, I think everything is coming together very nicely. But after wiring everything up and doing some initial tests, I did actually run into two issues which I needed to debug. The first was an intermittent communication issue with my PC. And this actually just turned out to be a problem with a really long no-brand USB-C cable that I was using. In the end, I just switched to a shorter 2-meter IKEA made one, and the problem just went away. And the second issue I was having was random unexpected triggering of the end stop sensors, which had me a little worried. It turns out that the non-shielded single wire I run back to the controller have a tendency to act as an antenna. I guess it's not really surprising. And given that I decided to use a pretty weak pull-up resistor around about 47K, that was getting quickly overwhelmed by all the system noise that those antennas were picking up and feeding into the microcontroller. Anyway, it was a very easy fix. I just changed the pull-up resistors to be something more aggressive. I think I used about a 1K resistor, and the problem immediately went away. Alright, and now for the fun bit. I'm going to talk about the control software that I'm using and the settings that I used in the firmware of my CNC. Now, up until now, I've been using a program called Candle. I think it's Candle version 1.0 or something like that. And really, it's actually pretty good. It's very solid, very responsive, and the graphic preview is really nice. I like it a lot. I did have the occasional stoppages when I was using, but I believe this comes down to a problem with the very slow Atmega 328p microcontroller I was using. I don't think it was an issue with the Candle software itself. Unfortunately, Candle is actually too simplistic feature-wise, and I actually need to use a lot of macro buttons going forward with my new controller. Otherwise, it's really just too much of a hassle to use, and it increases the chances of me making mistakes along the way. Now, I did look around for some alternatives, and apparently there is a new Candle version 2.0 out there, but it seems to be a fork made by someone that's not the original maker of the Candle software. So it seems a bit sus, and it doesn't seem that popular, so I decided to not go down that route this time. In the end, I actually ended up using a program called Universal G-Code Sensor, or UGS, as I'll call it going forward in this video. Basically, I chose it because it's the first one that I downloaded that was free, and it had the features that I needed, and it seems to do the job. But in all honesty, it's an awful implementation. It's terribly slow to load when you try to start it. It's slow to operate, it's super laggy, the graphics preview is awful, And it simply just crashes sometimes when you do certain things in the wrong order or something like that. Actually, it is really quite a bad implementation. I'd like to say it's a great example of how not to write code. All focused on features, but forgot about stability and performance along the way. Oh, I guess there was a second rant in this video after all. Alright, I promise no more. Anyway, it does the job for now, and it's free, so it really is hard to complain. And I know someone has probably put a lot of hard work into making this piece of software. So in that regards, I must say that I'm truly grateful for their efforts, that's for sure. And if I'm really honest, the more I use it, the more I generally sort of like it, I guess. I just need to switch my mind off with regard to the persistent lagginess, that's all. But really the big thing for me is having all of those macro buttons. It's even more critical with this new CNC build because now the PU settings that I'm using are different for the laser and the spindle. And so I really need a button to switch between two different settings modes. Now here down the bottom you can see all the custom buttons that I created and they all working fine. I'll actually put a copy of the code for each of these buttons in the video description for anyone who might need some help with making similar buttons. So that's it for the grblHAL controller software discussion. Let's take a look at the firmware settings. Now just flash on the screen here the original settings for the old CNC3018 that I was using. It looked like this. And as you can see, it's a pretty sparse affair. And here are the settings for the new controller. It looks like this. And as you can see, there are literally like twice the number of settings available. So let me show you the changes to settings that I've made. Now first we'll discuss the common ones, but later on I'll also show the specific settings related to the laser and the spindle modes that I'm using. 20 is set to on to enable the soft limits or the software control limits. 21 is set to 3, which turns the hard limits on in strict mode. 22 is set to 253, enables the homing cycle. This is actually 8 separate bits here, which I'll quickly show on the screen here as well. There's probably too much to explain here, but again, this is a setting that works for me. And unfortunately, this is where UGS again lets us down a little bit. It is unable to actually detect that the homing cycle is enabled, and it actually disables the home button, so you can't press it. So I actually needed to add that to my macro button list as well. I guess it's probably only looking for a 0 or 1. It's pretty fundamental stuff if you ask me, but anyway, whatever. 23 is a bit fill for inverting the direction of the homing for the X, Y, and Z axes. So it looks like I'm inverting the Y and the Z axis in this case as it's set to 3. 24 sets the speed for the precise part of the homing cycle, which is the second part, and I have it going real slow at 15 millimeters per minute. 25 sets the speed for the first part of the seek cycle or the homing cycle, and I have this going pretty much full bore at 1000 millimeters a minute. 26 is the debounce in milliseconds for the homing cycle, and I have that set to 10 milliseconds, and that seems to work fine. 27 is the homing sensor pull-off distance, and thankfully for my precise sensors, I only actually need to pull off a 0.5 millimeter to safely clear the sensor contact. Settings 100 through 102 is the steps per millimeter for the X, Y, and Z axes. Now for this, I actually increased the microstep settings on the stepper motor drivers to the maximum. So the old CNC only had around about 800 steps per millimeter, but here I boosted that up to 3200 steps per millimeter. I think the idea here was to try to increase the precision or the resolution if I could. And I've also naturally fine-tuned these to the actual dimensions of the lead screws. Interestingly, the X and Y axis lead screws that I bought new recently actually were pretty close to being bang on, just 0.05% under, or you could say 0.15 millimeters over 300 millimeters movements difference. That's pretty good. The Z-axis lead screw, however, is recycled from my original CNC3018 X-axis lead screw because I needed a longer one. And unsurprisingly, the amount of error here, it's the same as the old CNC was. It's just around about 0.44% under, which is like 10 times worse than the new ones. Anyway, it's nice to know that I found a store on AliExpress that sold somewhat in-spec lead screws. So I'll take a win on that one. Settings 110 through 112 is the max speed that the rapids can operate for each of the X, Y, and Z axes. Basically, I try to set this as fast as it will go without losing steps or having the lead screws making a racket. In this case, I got it up to around about 1100 millimeters per minute, which is only actually a slight increase over the original 1000 millimeters per minute, which I had with my old CNC3018. But I did notice when I was actually tuning this adjustment that the rebuilt CNC was not actually losing any steps. It was just making a lot of noise when it sort of gets to that fastest limit. The original CNC3018, when it actually got to its speed limit, you could actually hear it losing steps as well as the lead screw noise. So it seems that the hardware aspect of things is actually improved. The limitation just comes down to the lead screw system itself. Settings 120 through 122 is the acceleration rate in millimeters per second squared for the X, Y, and Z axis. And I'm using 500, which seemed to work fine, and it seems to give pretty fast acceleration. For my original pre-rebuilt CNC3018, I had this set as high as 1300 for all of the axes. There's no way it was accelerating faster than my rebuilt one, that's for sure. So I don't really understand why the setting difference is so different. Maybe there's something different in the firmware itself. I really just don't have any idea. Settings 130 through 132 is the maximum travel settings for the X, Y, and Z axis. And actually, I think this is the interesting one because this is the actual available movement range of the CNC that the soft limits use. And at least this gives us one easy metric to measure the actual improvement of my rebuilt CNC compared to the original one. The x-axis is 298 millimeters now, up from 287 millimeters, so a 3.8% improvement. The y-axis is 219 millimeters, up from 176 millimeters, so a pretty large 24.4% improvement. The z-axis is 83 millimeters now, up from 67 millimeters, so again a pretty good improvement of 23.9%. And if we combine these figures to get a volumetric figure, the size has now gone up to 5,416.7 centimeters cubed, from an original 3,384.3 centimeters cubed. So that actually gives us 60% more space to work with. So that's actually a pretty good improvement overall, I think. Next up, we'll take a look at the settings that need to change when I switch between using the laser and when I'm using the spindle. Setting 32 is really the basic one. It is set to 1 when using the laser and 0 when using the spindle. The main point of the setting is to be able to automatically force the laser off when doing rapid moves. Otherwise, you're going to get those unwanted burn lines when you move from area to area between operations. The PWM and speed control settings, however, are a little bit more complex now that I need to use a separate ESC for the spindle. And the reason is because I need to use the same PWM signal line for both the laser and the spindle. But the format of the PWM signal for each of those types is actually quite different. I don't really know how the original controller managed this problem. Maybe because it was just a simple DC motor controller, the same PWM signal could be used to drive both the laser and the spindle. I guess that's a possibility, that's for sure. Anyway, let's take a look at the settings for the laser first. 33 is set to 5 kHz for the PWM signal frequency, and you really want this as fast as possible to ensure that the laser switching speed is as fast as possible. Now the laser PWM signal just simply operates between 0 and 100% duty cycle. So 34 is the PWM duty cycle when it is stopped or switched off, so 0%. And 35 is the low PWM duty cycle, and again, same here, 0%. And 36 is the high PWM duty cycle, or fully on, so of course 100%. The low and high PWM duty cycle values are then proportionally mapped to a low and high spindle RPM setting. This is actually what the G-code S command uses to deliver the appropriate duty cycle for the required power level. And the settings look like this. 30 is the maximum RPM, set arbitrarily to 10,000, which is 100% laser power level. 31 is the minimum RPM, and I set this simply as 0, which will completely turn the laser off. And when we're in the spindle mode, the settings look like this. 33 is set for a 200 Hz PWM signal. In actuality, most hobby radio-controlled servos and ESCs typically operate on a 50 Hz signal, but I found that my ESC could safely cope with the faster 200 Hz signal, so faster the better, right? Unfortunately, figuring out the PWM duty cycles for the spindle is actually a bit of a tricky thing to do. The typical RC servo signal operates, I think, from around about 1 millisecond pulse width to 1.8 millisecond pulse width. I think it's something like that. Anyway, the fact is that it operates on a fixed time duration typically, and so that needs to be converted back into a percent of duty cycle based upon the frequency you're using. So it's a little bit tricky. That's what I'm trying to say anyway. So anyway, the numbers that I came up with based on the 200 Hz signal is for 34 PWM duty cycle when it is meant to be completely stopped, I set as 21.9%. 35 is the PWM duty cycle when running at the slowest possible speed, and I set that as 24.8%. So at that speed, it would actually be ticking over or moving. And 36 is the PWM duty cycle when running at the fastest possible speed, which I set at 34.1%. For the operating speed / RPM range, it's all just a bit of a guess for now because I don't really know what the RPM of my spindle is going to be. But in any case, 30 I set as the maximum RPM to be 10,000, and 31, the minimum RPM setting, is set to 250. Now maybe I'll adjust these RPM figures later, but I guess it's more probable that I'll just leave them as is. It all gets a bit too confusing having all different ranges to work with for the laser and the spindle or different types of spindles, so just keeping this simple 0 to 10k range is pretty much the easy way to sort of deal with it. And that's pretty much everything I changed, but there are plenty more settings there to play with, that's for sure. But if it's doing what you need it to do, generally I probably don't recommend playing around with it too much. That's going to wrap up this video. I doubt many people lasted to the end, but hopefully it has some useful information in there for someone. In the next episode, I will show you how I made a fully DIY brushless motor spindle Personally, I think it's one of the more interesting aspects of this whole build, so I highly recommend you join me for that one. So, as usual, I'll see you then.